Can I open the note? Okay, let me share. Okay, this is what we left last time on hydrogen oxygen mechanism. This is still in chapter 4. Okay, H2O2 mechanism. We have, okay, let me go back. Okay, this is the reaction rate for multi-step mechanism on hydrogen and oxygen reaction mechanism. We have 4 reactions, R1, R2, R3, R4. So we're gonna continue from here, okay? Right. Okay, good afternoon to all of you. Okay, let's consider this reaction again, hydrogen oxygen reaction, okay, mechanism where we have 4 elementary, what we call multi-steps mechanism. Reaction 1 here, reaction 2, reaction 3, and reaction 4. Okay, well, this is just representation of the real mechanism. Only 4 is considered at this moment. And as we've been gone through previous lecture, that if you want to know the net rate of production for each species, how many species are there? There are, I think, at least 8 species. Okay, and for oxygen, we have to consider all the forward and reverse reaction. Okay, some will give you positive, some will give you negative. So this is a net rate production of oxygen. Okay, and then we can write similar expression for each species, not only oxygen, but whatever you see in the mechanism. Okay, oxygen, hydrogen, HO2, single H, single O, OH, H2O, okay, and M, okay. So we have, this gives us what we call first order ordinary differential equation, right? And we also introduce you towards compact notation. Yeah, compact notation, writing them in a compact way, because since in this case we have only 4, but for many reaction, elementary reaction, more than 4, maybe 300 or 500, so we have to simplify, okay, the notification or the notation. So that's what we call compact notation. Okay, so here is the each elementary step, that means each one of these, 1, 2, 3, 4, okay, can be represented by this compact notation. Single prime is for reactant, double prime for product. And just like if you take the first reaction here, this reactant, this is your product. So this is single prime, this is double prime. Okay. So, and if we have many, okay, elementary steps, so you can repeat to write in this form from 1 till, for example, how many? 4. You have 4, then you have to write 1 till n equal to 4. I equal to 4. Okay, I is the species. Okay, I is the reaction, G is the species. Okay? I is the reaction. We have 4, reaction 1, reaction 2, reaction 3, reaction 4, and G for the species. How many? 8. Okay? 1, 2, 3, 4 until 8. Okay? J is 8, and I is 4. Okay, with this one is stoichiometric coefficient for reactant and product. All right, so we can write the stoichiometric coefficient matrices like this. Okay, for example, for the first reaction, this one, this is for the reactant, this is for the product. Reactant, yeah, for example, for the first reaction, H2O2, yeah, H2O2 for the reactant. Okay, H2O2, that means 1 and 2, here 1 and 2. And for the product of first reaction, we have HO2 and H. HO2 and H. So HO2 here and H, which is number 4 and number 6. So number 4 and number 6 in the product. Number 4 and number 6 for the product. So similarly, we can write same thing for reaction number 2, reaction number 3, and reaction number 4. So we have 4 reactions. Okay. And the net production rate of each species, meaning for example, we take the first one, the oxygen. Net rate production of each species, in this case oxygen. So this is the net. Yeah, some are positive, some are negative. So this can be simplified by using this notation. This one. Okay. For each these three relations, the three mean the one previously, compactly express the net production rate of each species. For example, for the first, so that means here is J species. How many? There are 8 of them. You have 8 of these. Yeah? Each one represent one species. Yeah? For example, if J number 1, yeah, for the species number 1, which is oxygen, J2 mean hydrogen, J3 mean H2O, J4 mean HO2, 5 oxygen, 6 hydrogen, 7 OH, and 8 M. Okay, and this just a compact notation where Q is VJI is the net between reactant minus product, chromatic reactant minus product, and Q is the net production rate for each species. In this case, J1, J1. Repeat for J2, J2. Repeat for J3, J3. Okay? And the Q, the W dot, nanti kalau omega dot, this is called net production rate. Okay, let me comment. I have to maybe reduce this so that it can go down. Not this one. This guy. Comment. Okay, let me. Okay, here is the net. And to write, it can write my finger, but not using this pen. The net production rate of each species is this guy. Okay, and then for each species, and then the Q stands for the rate of progress variable. Okay, the production rate. Yeah. Of each species is called W dot J, and this one Q is called rate of progress variable. Just the name of it. Variable. Okay. The Q is the rate of progress variable. Okay. So, okay, for example, for let's say, okay, for equation, the oxygen, for okay, CO2 dt, okay, we have equation, the one that you see earlier. This, yeah, this one. DO2 dt for the first species. Yeah. Okay. And then you can write the Q. Okay. I in this case stands for oxygen. So we have all those Kf, I, O2, H2, H2O, HO2, O, H. Let me open the text, so that you can see. Page, if you look at your textbook, page 118. Put it up. Okay. Oh, it's a different book. Presentation. Do you see this? Okay, here. Let me enlarge. Oh. Do you see the textbook or no? Huh? Yes or no?
No.
No. Oh. Let me open using this software. Do you see now?
Yes.
Okay. Yeah, this one. Okay. The production rate, which is omega dot J, correspond to the left-hand side of equation 4.26 and 4.27, for example. Okay. All right. For example, for reaction number one means this reaction. H2O2, HO2H. Right? And for, let's say, for the first species, oxygen, yeah, for the first species of oxygen, okay, this is the first oxygen and hydrogen, yeah, oxygen and hydrogen. Then HO2 and H. HO2 and H. So O2 and H2 to the power of 1, that means still maintain there, but the rest are to the power of 0. I mean they have 8 species, they write it together. Okay, but for each other species which is not involved in the first reaction, just put to the power of 0. So it does not matter, okay? Only these two. And this is the reactant. And then the product, we have HO2 and also H. Okay? So eventually become like this. KF1 O2 H2 minus PR1 HO2H. So this is your QI. Let's correspond to the, they call it rate of progress variable. Okay? For the ice elementary reaction. In this case, ice means the first one, elementary reaction. And sigma, what is this? Stands for pi, big pi. It's used to denote the product of term in the same sense. And summation is to present a summation of terms. Okay? Right. So writing similar expression for, okay, I 2, 3, 4. The first one is here. Number 2 is this reaction. This number 2 is I number 3, I number 4. Okay, I number 4. Okay, 1, 2, 3, 4. One, two, three, 4. Right. The compact notation embodied in equation 4.29, 431, 434 is particularly useful for solving kinetic problem using a computer. The software ChemKin is a what? General purpose package for solving chemical kinetic problem and is available through Sanja National Lab. So this is software that using this kind of notation so that it becomes easy for you to trace each one of the reaction. Right. Let's go back to this reaction mechanism. Okay. Okay, relationship between equilibrium constant with the K. K is the rate coefficient. Okay. Equilibrium constant stands for the global reaction. Yeah, the global reaction. Okay. And the small k stands for equilibrium rate coefficient of each reaction. Okay. Okay. For bimolecular reaction means such as this. Let's say A plus B okay, forward and reverse. Okay, producing C D, okay? C plus D. Okay, so for let's say for species A, okay, yeah, for species A, dA dt equal to okay, minus Kf AB Okay, because for A, forward mean A becoming A and B becoming lesser, so it's become negative. And for the reverse, it's positive. Okay, R reverse is one. Actually, don't need a number one because it's only one reaction here. You have a C and D. Okay, C and D. Okay, at equilibrium condition, what is equilibrium? Equilibrium means when the forward reaction and the reverse reaction equally the same. Forward and reverse is equally the same. So there is no net rate of change of species A with respect to time. Okay, so dA dt is equal to 0. So 0. Okay, at equilibrium. Okay, forward. Actually, in chemical reaction, you always have forward and reverse. But if the forward and reverse reaction, they are all at the same rate, so meaning there's no net rate of change of the production of or the destruction of that species. Okay. Alright, so dA dt will become 0. Okay, dA dt will become 0. So then we have only the balance between these two, these four species. Okay. At equilibrium for a bimolecular means two molecule acting together. We can rearrange the reaction rate to get that means CD so it's equal, so negative become this KFAB equal to KR1CD, right? So CD over AB equal to KF over KR, right? We can also define equilibrium constant based on molecular concentration. Kc is what we have seen in previous chapter. Yeah, Kp is the equilibrium constant overall. Yeah. So if you have only one reaction here, the Kp, okay, is equal to Kc RUT over PO, and C plus the C is the stoichiometric coefficient that there in front of here is small a, small b, small c, small d. Okay, so this is the on the top. Okay, so you have this Kp, the Kc RUT over PO. Okay, right. So for the forward reaction and reverse reaction here, this one, the forward and reverse, this is equivalent to KCT, which is the same thing. So you can here. KF over KR, KF over KR is equal to KC, which is KC is equal to CD AB to the power of this one. So therefore, this one equivalent to KC, this one equivalent to KC, right? KC, and this one equivalent to KF, KR. Just rewrite. So this is the equilibrium constant. Okay, equilibrium constant. The capital one is equilibrium constant. The small one is the rate of reaction, forward and reverse. This is true for bimolecular reaction. Most of the time, our reaction is bimolecular. In this case, for example, like this one, this is bimolecular. Two molecule, okay, producing another two molecules. So it's a bimolecular reaction. Bimolecular reaction. And this is for during equilibrium. During equilibrium. Okay. Example 4.2. In their survey of experimental determination of rate coefficient of NHO system, Hansen and Salmian recommend the following rate coefficient for the reaction. This is a one-step global reaction NO plus O. producing NO2, where Kf which is equal to this one. Determine the rate of Kr for the reverse reaction, this one, at temperature 2300. Okay. The forward and reverse rate reaction are related to the equilibrium constant Kp via equation 4.43 just now. Okay, so we have this. So now we have come up with this Kf over Kr equal to Kc. So to find the Kr, to find this one, we require you to evaluate Kf and Kp. Kf, this guy, and also Kp at temperature 2300. Okay, and we know Kp, yeah, which is the rate, the equilibrium constant, okay, based on our second chapter, is equivalent to exponential minus delta G capital at GT over RUT. With delta G, it depends on your reaction at that temperature. Okay, right. Our reaction is this reaction. Okay, so therefore we have nitrogen, oxygen minus Gibbs function, NO, and also oxygen at this particular temperature. So this delta G, you can look at table at the back of the book, which is related to A8, A9, A11, and A12. So put all the values there based on temperature 2300. This temperature 2300. So yeah, every of this is written here. Why this oxygen is 0? Because it's 0 at every temperature for this one. So 61, this one is 101. So we have delta G equal to 163,461 kilojoule per kilomole. Therefore, Kp, Ru is 8.314. Temperature is what you see here, 2300. Kp is equal to 1.94, 10 to the power negative 4. Okay? Right. So the forward reaction, which is this, they give you the equation there. Okay, so evaluate that based on what given in that particular question. So Kf is equal to 3.8 time temperature 2300 exponential negative 2820 over temperature, which is 2300. So Kf is 1.04 times 10 to the power of 9 centimeter cube per gram mole second. Okay, so your K reverse, so K forward is already evaluated as this value. So K reverse is equal to Kf over Kp. Kp you got it already here, 1.94 times 10 to the negative 4. So you just put it there. In that K reverse equal to 5.28 times 10 to the negative 12 centimeter cube per gram mole per second. So this is the example of this particular reaction. Okay, example 4.2. Right. Okay, steady state approximation. Okay, steady state approximation. Usually, after a rapid initial buildup of radical, it is destroyed as rapidly as it is formed. So rate of formation equal to rate of destruction. So this is what we call just now also steady state. Yeah, steady state. Analysis can be simplified by analyzing the steady state approximation to this radical. Okay, to this radical. This is an example. You can go through this example. Okay. Right. Just to this example, just asking you what is N, what is N, what is that? This is the order of reaction. Okay. You can take a look at the example. Okay. Example 4.3. Okay. It's there in the book. Okay. Chemical time scales. Right. Time scale. We actually we have to also talk about time, because so far we just talk about concentration, destruction, or production and destruction. Okay. However, there is another element in the chemical kinetics, which is time. Which is time. Okay. The time scale for chemical reaction. Chemical time scale. There are two. One is in terms of concentration. The other one is time, because you see this D whatever concentration, let's say X, okay, over D. This is concentration, this is time. Okay. And so far we always talk about steady state, meaning time does not important. Okay. But actually time is important, right? It is a time scale. So the, the time scale can be used in comparison with mixing and convective time scale to see which effect would be the major factor in governing the combustion process. Sometimes mixing is important, sometimes convective time scale is important. Okay, actually for reaction to start, we have to have a fully mixed molecule, or species at molecular level. So if mixing has been done prior to the combustion, prior to the reaction, so mixing does not important. Okay, this is normally important true for we call it pre-mix fuel and air. Pre-mix means before combustion, fuel and oxidizer already being mixed at molecular level, so no issue of mixing. Then what's left? Left is only chemical reaction. Okay, chemical reaction, which is the change of concentration with respect to time. Okay. However, sometimes mixing is important because it has not been mixed thoroughly yet. So which one is faster? If mixing is take longer time, so the reaction is governed by the mixing rather than chemical time scale. Okay, and this is true normally for diffusion flame. In diffusion flame, fuel and oxidizer not yet been mixed thoroughly. They are progressing. The mixing is going on. Okay, so that's why mixing, they said here, you have to compare between which one, mixing or time, convective time scale. Okay, to see which effect would be the major factor in governing the combustion process. Okay, kinetically control combustion, mixing control combustion. If mixing has been done faster, so mixing is not controlled, does not control the combustion process. It will be controlled by kinetics, yeah, of the which is chemical process of the combustion aspect. Okay, so the slower process will control the reaction. The slower process will control the reaction. Which one? Kinetic or the chemical or the mixing? Which one will? The slower is the one that control. Okay? For example, if you have 4 children, I'm always relating to a big family. If you want to go somewhere, if you want to go to for journey, all three, there are 4, all three already in the car, but this another fella, which is maybe the youngest normally, or maybe the eldest, depends, hasn't prepared yet to enter the car, still at home, still in the house, so everybody has to wait for him, isn't it? Because of him, the genie was late because of him. So he controlled the whole event. The last person is the one who controls the whole event. It's the slowest. Okay, so just an example. Okay, reaction rate are integrated and ratio of final initial concentration given to solve for time involved. Reaction rate is a differential equation of the species concentration. That's what we see here. The differential equation of species concentration. Okay, so we need to solve this differential equation. Okay, We need to solve this differential equation. Right, for example, let me write something here. Okay, for unimolecular reaction, unimolecular reaction. Okay, unimolecular means only one. Molecular. Okay, let's say A. They are producing product. A producing product. Okay. So negative dA dt for this particular reaction is equal to d product. What they are, they don't spell it out. Just put in writing over dt. Okay, let's say it's equal to K. Okay. Okay. Like that. Okay. Okay. So we have to integrate this equation, the one you see over there. Okay. Put together dA over A that you see on the right side. Okay. We are referring to this one, right? So K equal to negative. Here is negative somewhere. Okay, negative here. Oops. Okay. If K dt, you bring the concentration on one side and the time on the other side. Okay. So yeah, you see here. This is concentration. This is concentration. Bring down and dt. Okay, k dt. Right. So you integrate left and right. Okay. And from there you can get let's say log A, which is equal to negative. Okay. Let's say log. You can see that negative k. Okay. Time. Okay. And this is evaluated from early concentration, meaning before reaction happened, initial, and the concentration after some time. Yeah. After, let's say, oops. The time after time t. So therefore, go on A B okay, forward, long, ln ATOAO. Okay, equal to negative, okay, K. Okay, so there you go, the time is there, all right? So now natural log means e to the power of negative this value e equal to a, okay, at any time given to a initial, the concentration of the species A initial. Okay, so this is what it refers to 1 over e in the, okay, I just write it as 1 over e there. Okay, where 1 over e is equal to exponential, okay, this one is exponential, okay, in the bracket a minus k, okay, and this is called tau. This is what they call the time scale, yeah, chemical time scale, okay? Chemical time scale. So you can solve for t, the time, okay, for the time. So there is how the time comes into play in this concentration, okay, for unimolecular reaction, unimolecular reaction. Okay, for bimolecular reaction, okay, for bimolecular reaction, we have also we can also solve this the same way. You can also solve the same way, right? Reaction rate are integrated and ratio of final and initial concentration given to solve for time involved. Reaction rate is a differential equation of the species concentration. Solve this differential equation. That's what we see here. We need to solve it. Characteristic time scale, T chemical, this guy, this tau chemical here, the T chemical, we call it characteristic time scale. Okay? Characteristic time scale. Okay? Time required for concentration A to fall to 1E of its initial concentration. Okay? Time required for concentration A, okay, concentration A, right? Concentration A, which is this color, this time required for the concentration A to fall, okay, to 1E of its initial concentration. Okay. Other commonly used time scale is half-life, yeah, which is time required for concentration to fall to 1/2 of its initial value. That means, let's say, if A have certain concentration, let's say 1, just an example, how long it takes for the A to fall from 1 to half? This is called half-life. Yeah, half-life. Yeah, half-life. Okay. So that's the time scale. Yeah. So it depends on what you are dealing with, what kind of reaction you're dealing with. Sometimes, most of the time, okay, the main governing problem is uh, the chemical, yeah, chemical concentration reduction. Okay. Okay, let's take a look at next chapter, which is chapter 5, some important chemical mechanism. Okay. Chapter 5, huh? Yeah, this one. You see this, chapter 5? Chapter 5, some important chemical mechanism. Chapter 4 talk about chemical kinetics. Okay. Chapter 5 is some important chemical mechanism. Okay. Our approach in this chapter will be to present or outline elementary steps involved in a number of chemical mechanisms of major importance to combustion and combustion generated air pollution. Okay, for detailed discussion of this mechanism, the reader is referred to the original literature, reviews, and more advanced textbook that emphasize kinetics. Okay, there are many, in fact, many courses that only focus on kinetics alone. Our coverage on kinetics in this particular subject is just a shallow, or just giving you some flavor of it. Okay, just a small portion of it, very, very small portion of it. If you need to go into detail, you can refer to this reference 1 and 2. Here, of course, is simply to illustrate real systems which are generally complex. Normally, okay, the reaction, a chemical reaction is very complex. It's not easy. Normally, generally complex. And to show that the fundamental discussed in this previous chapter are indeed important to understanding such system. Okay? Right. One of the basic important system is H2O2 system. When I did my master in Leeds University on fuel, they call it combustion and energy, combustion and energy master degree, I just wondering why they keep on repeating this mechanism. H2O2, H2O2, H2O2. And then if you go to the lab, they give experiment also on hydrogen, oxygen, hydrogen, oxygen, hydrogen, oxygen. They have a few, for example, mixed reactor. So they put hydrogen, they put oxygen. They put hydrogen, they put oxygen. So actually, this is one of the most researched fuel, hydrogen, oxygen. Yeah, hydrogen, oxygen. On top of methane, CH4 and oxygen, or CH4 and air, in real combustion, close to real combustion, is methane plus air. Methane plus air, because methane is widely abundant in the real world. Okay, anything decomposed producing biomethane, which mainly methane plus some carbon dioxide, CO2, and also hydrogen sulfide plus moisture, H2O. Okay, we have gone through many examples before this on methane plus oxygen, air, mixtures. And then for if you want to go into detail of kinetic of pure fuel, this is what they normally refers to, hydrogen oxygen. Okay, you'll see how important this system. In fact, my current research is on rotating detonation engine. They also use hydrogen and oxygen system. Let's say this is your oxygen tank. Okay, this is your hydrogen tank. Okay, this is, let's see, oxygen. This is hydrogen, and then they're connect together and they put in the system called. Recently, I just, if you're interested in this type of study, Japan launching the first RDE system into orbit, not orbit, but in we call it application on rocket. Because RDE, rotating detonation engine, is one of the advanced system, okay, where they predict it will become a major propulsion system in the future, okay, which is very efficient using detonation mode, rather than deflagration mode. And that test was done by Professor Jiro Kasahara from Nagoya University, with uh, collaboration with JAXA, Japanese aerospace industry, equivalent to NASA, National Aeronautic and Space Administration for America. JAXA. So the last month they successfully developed the technology and use it for outer space application. Oxygen plus hydrogen, okay, and they put in RDE system, rotating detonation system, okay, producing thrust for about 500 Newton. However, it can only last for 6 seconds. On astounding rocket, they call it astounding rocket, mean rocket that, okay, launch originally using normal propellant, but once it goes into the orbit, they this what do you call the main system detach, and then the RDE goes on. So RDE system, okay, goes into orbit. I mean, not outer space, around yeah, the high sky, okay, and it run only for 6 seconds to produce thrust for about 500 Newton, 500 Newton using hydrogen oxygen fuel. Okay, right. So here is the mechanism. How many? H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 until 20. Yes, 20, yeah. Right. Hydrogen oxygen system is important in its own right, okay? Especially in rocket propulsion. Yes, exactly. Okay, rocket propulsion. Actually, this type of propulsion has been researched by many agency, NASA especially, JAXA, yeah, uh, Korean, yeah, of course Chinese, Russian, okay, right. But RD is one of the most latest type of engine, okay. Right, this system is also important in subsystem in oxidation of hydrocarbon and moist carbon monoxide. Detailed review, okay, can be found in literature 3.5, relying heavily on this reference. Glassman, we outline the oxidation of hydrogen as follow. Glassman is combustion textbook, okay? Irving Glassman. Can refer to that book. Okay, we have initiation, very high temperature, and then other temperature, chain reaction, step involving OH and OH radical. Okay, chain reaction means from one radical split or producing more than one radical. For example, one radical, which is hydrogen, producing two extra radical. That's called chain branching or chain reaction, chain branching especially. Okay, O producing HOH. Okay, OH producing H2O and H. These are radical. Okay, this one producing another hydroxide. Yeah? This is called chain branching. Okay, and then chain terminating, which means from two radical, okay, to become nothing left. No more radical. This is species. Okay, this is third body. Two radical until become no radical. There's no radical here, right? So this is called chain terminating. And we need to include reaction involving HO2, the hydroperoxide radical, and hydrogen peroxide. Okay. And then become active, and following reaction reverse H2 come into play. Here, and then here, until 20, okay, 20 elementary, we call it elementary reaction, right? So how many species there? You can check yourself, how many of them. Okay, depending upon temperature, pressure, and extent of reaction, the reverse reaction of all the above can be important. Therefore, in modeling H2O2 system, as many as 40 reactions, just now it's only 20, okay, can go up till 40, can be taken into account involving 8 species. Okay, The H2O2 system has interesting explosion characteristic. This is shown in figure 5.1. That can be explained using above mechanism. Figure 5.1 shows that there are distinct regions in temperature pressure coordinate. Where there are. This is what I did during my master degree. One of the lab experiment is to map this what you call detonation explosion limit. Okay, explosion limit. Okay, this is explosion limit or a stoichiometric hydrogen oxygen mixture in a spherical vessel. You have a vessel, sphere vessel like glass vessel. They put hydrogen, they put oxygen, and then ignite, and then boom. Yeah. So they check how much pressure, and then the temperature for that reaction. So they produce what we call this S limit, explosion limit, like an S curve here. Here the S curve, right? Okay. Figure 5.1 shows that there are distinct regions in temperature pressure coordinate where stoichiometric mixture will and will not explode. The temperature and pressure correspond to the initial charging condition. The spherical vessel containing reactant. To explore explosion behavior, let's follow a vertical line, say 500 degrees Celsius. Okay, let me go to this. Do you see this? Right. Explosion limit of H2O2. Okay. Okay, this is chapter 5, reaction mechanism, analysis and some important mechanism. Analysis of reaction mechanism, sensitivity analysis, identify the rate limiting reaction step. Reaction pathways analysis, determine the characteristic reaction path. Eigenvalue analysis, determine the characteristic time scale, direction of the chemical reaction. Reduce mechanism, from info above can eliminate unimportant reaction. You can eliminate some reaction which is not important. Generate simplified or reduced mechanism for faster computation. Because if you want to involve all those elementary reaction will take a long time for you to solve. So you have to somehow reduce it. Okay, the explosion limit, H2O2 system, hydrogen and oxygen system. Here they have 20 steps. Okay, right. So then producing this curve. See this curve. Let's follow 500 degrees Celsius. Okay, the vertical line is pressure. The horizontal line is temperature. So P and T. Okay, P and T. So here is, let's follow 500 degrees Celsius line. Let me follow vertically. So here is the first limit. This is the second limit. This is the third limit. Here, no explosion. Here is explosion happen. This one is no explosion, and this one there is explosion. So no, yes, sorry, no, yes, no, yes for explosion. So if you follow temperature 500, not necessarily the mixture will explode. If you are at this point, that means at this pressure, slightly above 1 atmospheric, no, here is a millimeter mercury, okay, 1 point, let's say 1.3, at this particular temperature, it will not explode because you are in this region. However, at the same temperature, but you increase the pressure, initial pressure, before combustion, you increase it, let's say to 2. Then you see the mixture will explode this point. If you further increase the pressure initial until to this point, let's say 50 millimeter mercury, before 50, it will still explode. Above that, let's say 60, there's no explosion. Here, there is no explosion. This is no explosion. If you further increase the pressure to this point, 2000 millimeter mercury, no explosion. But if you pass this point, let's say 4000 millimeter mercury pressure, yes, it will explode again. Okay? So this explosion, E explosion, no explosion. There is another explosion limit here. And here is no explosion. Yeah, no explosion. What does that mean? Meaning, if you deal with a tank container, let's say you work in industry, okay, in the tank, okay, there is fuel, yeah, there is fuel, and air is always available, maybe inside, maybe outside. If you deal with temperature inside the tank for oxygen, for hydrogen oxygen mixtures, you have to be careful. Sometimes, if the pressure and temperature is within this explosion limit, okay, if you have already oxygen, you have already fuel. You just wait for one more, which is ignition. For example, you are trying to let's say drill the or do some kind of repair on the tank. Yeah. If you try to cut it or welding it, you have spark. So you wait for one more ingredient just before explosion. It's happened in many occasions where engineers or technician trying to repair a tank, which you do not know what's inside. That's why you need to let whatever gas inside the tank to be out first. To be safe, you refill with nitrogen. Nitrogen is inert, and then you can start do your repair. You can cut it, you can welding it, whatever. Okay. But if you are dealing with something you do not know, please be careful. You may it may go into explosion. If the pressure and temperature is on the right value, this here, this is explosion. This here, okay, this is 100 because it's quite high. Then if you deal with lower temperature, okay, it may not explode. But if you deal with 500, sometimes the tank is on hot sun. The temperature inside the chamber will be hot. Maybe you have some kind of reaction or some kind of heat transfer happen before that. The chamber is hot, so it may reach to this is hydrogen. For your you can careful with hydrogen. But if you deal with other fuel, which is maybe lead or whatever propane, so the air will not get the temperature. Hydrogen will get lesser temperature. Yeah, get different temperature. We have to be careful on that. Okay, here it says above 1.5 millimeter mercury, 1.5 above this point. Okay, this is explosion. It is like that. The action is the prevailing or important reaction that cause chain and changing. How explosion happen? When you have two species and then use multiplying and producing more radical at a very fast rate, very high and fast rate. Okay, very fast rate. This radical more than making the pressure to be suddenly goes up and then it causes explosion. Okay, so this radical produced in a very short period of time. This is what happened in above 50 millimeter. What is it here? Above this point. Okay, this point. Okay, no explosion. Above this point, this region, there is no explosion. Competition for hydrogen atom between H3 chain branching and H11 chain terminating. H3 and H11. H3 and H11. Branching and terminating. H3 branching, H11 terminating. Terminating means from uh, two or one radical to and then produce one more radical. Okay. Above 3000 millimeter mercury, here this guy, point, I mean this point, above this, there is another explosion region. No explosion, this point, there is explosion, no explosion, there is no explosion. So you have to know your S curve, okay, for whatever fuel you are dealing with. In this case, is example of hydrogen. Okay, new reaction activated and adds a chain branching step. When you add a chain branching step, so it may or will explode again. Okay, right. So that is hydrogen oxygen system. Okay, this is methane combustion. Talk about methane. Before this, methane mechanism is available as GRI MEG. Okay, at version 3 now, with 325 reaction and 53 species. 325 reaction. H2O2 40, but methane CH4 there are 325 at this particular time with 53 species involved. Just now only 8, I guess, right? But this one have 53 and 325 reactions mechanism, yeah, the reaction, 325 steps. Okay, each arrow shows set of elementary reaction, primary reactant at tail, primary product at head, additional reactant species along arrow, corresponding reaction number indicated, destruction rate of reactant in bracket. Width of arrow shows significant of the reaction. Width of arrow shows significant of the reaction path. Which one is important than the other? Okay. Each arrow shows set of elementary reaction. This one, this one, this one, this one, this one, this one. So each arrow shows set of elementary reaction. Okay. Primary reactant at tail, product, primary product at head, tail and head. Okay. Primary reactant at tail, primary product at head. Eh? Alright. So you can see here how many? How many of them? Reaction from 1 to 7, all this until reaction 153. 3. Okay. High temperature reaction pathway diagram for combustion of methane in a well-stirred reactor at 2200 Kelvin, pressure 1 atmosphere for 0.1 second residence time. Reaction numbers refer to table 5.3, while reaction rate are shown in parentheses. Okay, for example, 267 implies 2.6 and 10 to the negative 7 gram mole per centimeter cube second. Okay. So this one is low temperature. This one high temperature mechanism. This one is for low temperature reaction pathways. Below 1500, this one is more than, okay, or at 2000 or 2200 Kelvin. Okay, here. See how many reaction? Yeah, very many of them. Right. Let's check in the book whether they have it listed down. Yeah. Okay, let's continue. This carbon monoxide oxidation. Is an example? Yes, there have few example. Okay, few example. Let me check. Where is your methane? This particular. Okay, methane combustion. Okay, methane combustion. They have GRIMAC. Okay, this is just a mechanism. Now, okay, this example for methane combustion mechanism. GRIMAC 2.11. How many? 1, 2, 3 until 46, 47, 92, 93, 137, 138, 177, 178 until 219, 220 till 262, 263 until 279. So actually this is the previous one, not the latest one. The latest one 325, isn't it? This one. They keep on developing the mechanism. Okay. All right. Methane, as an example here, listed in this table, 5.3 complex methane combustion mechanism. This is the reaction number 1 to something, and this is the fourth rate coefficient. A is the Arrhenius number, B and E, activation at E, the energy. Okay, so right, so you can take a look at it. This is methane. This is only example of a methane gas. Methane gas. Right? Actually, the one that you see, the one at home, the stove, the lighter, the candle, the whatever you see alive in front of you, even though you see very easy to light up, actually within this very small time frame, they have this many reaction, elementary reaction. Okay? It's very complex. It's very complex. So here is the pathway. Okay, that mentioned just now. Right. Another important mechanism is NOx production. NOx. Nitrogen oxide of nitrogen, NOx, and OX. Okay, call it oxides of nitrogen. Just now is H2O2, the first one. You have an S curve as an example. Hydrogen, oxygen. Then you have methane, CH4. Okay, with oxygen. Okay, and then you have this NOx, oxygen, oxide of nitrogen formation. Nitric oxide in chapter 1 are more and more fully discussed in chapter 4 is an important minor species in combustion. Why? Because of its contribution to air pollution. This is the issue. Nitrogen is air that, species that there in air, 79%. Sorry, 79%. Okay, 21% is oxygen, 79% is nitrogen, N2. Right. Therefore, because abundance of nitrogen in the reaction, supposedly this nitrogen does not involve in the chemical reaction. Ideally. But in real world, it will always react. Okay. The detailed nitrogen chemistry involved in the combustion of methane is presented in the second half of table 5.3. In the combustion of fuel that contain no nitrogen, Nitric oxide is formed by three chemical mechanisms, okay, or route through involve nitrogen from air, thermo or Zaldovich mechanism, the Fenimore or Prong mechanism, and or to intermediate mechanism. This is growing evidence for possibility of post route involving that there is another possibility, but the main thing three thermal, or they call it Zaldovich mechanism, Prong mechanism, which is Fenimore, they call it. Why names that? Because these are the people who pioneer the mechanism, pioneering the mechanism. Okay, and the other one is N2O intermediate mechanism. There's one more actually, fuel NOx, but they eliminate this. They said this is containing a fuel that contain no nitrogen, so there's no fuel NOx here. Okay, thermal means temperature because of high temperature. As I mentioned, when you have high combustion at high temperature, beyond 1300 or 1400, okay, this N2 will dissociate, become single, unstable, and then join with other species to produce NO something. Okay, the thermal or Zaldovich mechanism consists of two chain reaction, O plus N2 producing NO plus N. See here, N, this N is a single atom N, which is radical that unstable and also combined with other things. For example, oxygen. Okay, to produce NON, single atom hydrogen, oxygen, which can be extended by adding the reaction to the of them. The rate coefficient for N1 till N3, okay, which is there are six of them, two forward, three forward, three reverse. One forward, two forward, three forward, and three reverse. One reverse, two reverse, and three reverse. So this value is obtained from experiment actually. Okay, what are the rate coefficient? This K, this value obtained from the experiment. Okay. This three reaction set is referred to as extended Zaldovich mechanism. In general, this mechanism coupled to the fuel combustion chemistry through O2, O, and OH species. Zaldovich means thermal, okay, right? So these are the main three. Fenimore, okay. Number one is thermal, or Zaldovich. Number two, Prong mechanism, which is Fenimore, pioneered by Fenimore. Okay. Okay, this guy, Fenimore mechanism. Okay. Then the other one is N2O mechanism. N2O immediate mechanism. This guy, intermediate mechanism. This is important in fueling. Okay. The Fenimore mechanism, or the they call it the second mechanism is shown here. It's quite complex. Okay, this is the production of NO associated with the Fenimore Prong. You can call it Prong. Okay, Prong NOx. Yeah, we call it Prong NOx. Okay, Zaldovich is thermal NOx. This is thermal NOx. Yeah, this one. Thermal NOx. Zaldovich is thermal NOx. Okay, this is Prong NOx. And the other one is N2O. 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 Okay. 3. So that's how the NOx is produced. Right. Okay. Yeah. Some important chemical mechanism. The one that you see on top methane, on top of that is oxidation of higher paraffin, alkane, it's carbon oxidation. After hydrogen oxidation system, they have carbon monoxide oxidation. Although the oxidation of carbon monoxide is important in its own right, it's extremely important to the oxidation of hydrocarbon. Okay, so here is your carbon monoxide mechanism, CO here. Okay, right? How many? We have 1, 2, 3, 4, 5, 6, 7. That's 7 for carbon monoxide. It's another dangerous, okay, product. Yeah, this is very toxic. 7 mechanism. Oxidation of higher paraffin. Paraffin or alkane are saturated straight chain or branch chain single bonded hydrocarbon with the molecular formula CnH2n plus 2. Right? He said that we're going to discuss about n more than 2. Okay? Right? The oxidation of paraffin can be characterized by 3 sequential processes given below and illustrated by the species and temperature distribution shown in figure 5.2. Species mole fraction and temperature of function of distance for the oxidation of propane in a steady flow reactor. Steady flow mean what? Steady flow mean if you have a reactor like this, steady flow mean reactant and product flows in and out steadily in open system. It's called steady flow reactor. Well-stirred reactor is a confined reactor which is closed system. Okay. So these are the examples. This is the example of C3H7 reaction. Sure, is it correct? Here, example of C3H8, example of others there. Single-step reaction parameters for use in equation equation 5.2 here. Global and quasi-global mechanism. Okay. If you have, remember we have always this kind of thing, CHY plus oxygen producing CO2 and H2O. So to find the rate of the CXHY, CXHY dt, this is the question, where the parameters A, EA, RU, and then N are shown in table 5.1. Table 5.1. This one, table 5.1. CH4, A, EA, RU, this your N, this your N. The formula is here. Okay, the formula is there. No, that one, this one. This one. Okay, so this is the formula. This is Arrhenius rate of reaction. Global, the global one-step reaction. Okay. Okay. If you deal with elementary reaction, you are not global, you are doing elementary reaction. Okay, let's check it out. I think we are towards the end of the lecture, where we have covered chapter 5. Okay. And then next, we're going to skip chapter 6. All right, we're going to go into chapter what we call premix. Okay, premix, I think chapter 8. our next chapter 7, sorry. Chapter 7, isn't it? I'm not sure about your version, your book. Third edition is chapter 8. Lamina Premixed Film. Okay. Alright. I'll assign you some homework for chapter 4 and 5. There's a few questions. And then you have to prepare for your final project, okay? Your final project, you have to group yourself. How many of you? 40 something? Maybe you can put yourself into groups of 3, okay? And try to propose something, okay, in your project. Okay, pick type of film you want to play around with and in which reactor you want to let them in and then react. Okay. If you deal with IC engine, maybe for example, this IC engine work with let's say natural gas. IC engine using gas IC engine. So you have that fuel enter with what? With air. So maybe natural gas plus air in the combustion chamber. Maybe you can probe into what happened in the IC engine, yeah, on that particular fuel, yeah, in the reaction. Try to come up with topic, okay, of yours. I was at the beginning. I have some idea. Okay, you propose something. I may also propose something. Okay, get together into 3 person in one group. Okay, form your groups, and then try to propose something. I also think about something. Project on combustion. Okay, project on combustion. Because we don't have final exam, we have a project. So yeah, start to think about the project from now on, because we have only few weeks left, yeah, before the end of the semester. Okay, I think that's all for today. Anything you want to ask me? Any question? No question? Are you there? Hello?
Let's get started. Drive safe.
No question? Okay, if not, I'll stop here, okay? And uh, that's all for today. So maybe we'll see you next time. Next meeting will be on what? Next Wednesday, isn't it? Okay, that's all for today. Okay, thank you very much. Thanks for listening. Okay, Assalamualaikum warahmatullahi wabarakatuh.